Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, Lecture 15, Predicting Eclipses. Now that we've learned what lunar and solar eclipses are, and we've learned that you have to absolutely go see a total solar eclipse in your lifetime, let's learn a little bit about how astronomers, both ancient and modern, could predict when eclipses would occur. Because, of course, today we can compile tables like this that could show you when total solar eclipses will occur hundreds, if not thousands of years into the future. And we can certainly predict when they happen thousands of years in the past. But the question is, how do we do this? How do we predict when total solar eclipses will happen and where they will happen on the surface of the Earth? And also, what are the conditions that have to be in place to get a total solar eclipse? And why don't we get a total solar eclipse at every new moon? So we're going to answer all of those questions in this lecture. So for now, let's talk about why it is that we don't get a total solar eclipse at every new moon. We don't get total solar eclipses at every new moon because the orbit of the moon is tilted by about 5 degrees with respect to the ecliptic. Now, 5 degrees doesn't sound like very much, but remember when we build a scale model of the Earth-Moon system that the moon is sufficiently far away that even a small tilt like 5 degrees will ensure that what happens is that the shadow of the moon misses the Earth. So during a new moon, the Earth passes either above or below the shadow of the moon, and at a full moon, the moon passes above or below the shadow of the Earth. So, because of this 5-degree tilt of the moon's orbit, and here's the important thing to remember, the moon is tilted 5 degrees with respect to the ecliptic. The Earth is tilted 23.5 degrees over with respect to the equator. The moon is closer to the Earth's orbit around the sun than it is to our own equator. And that gives us a hint, as we'll see later on in the semester, about where the moon came from. The best model that we have for the origin of the moon right now is the collision with a Mars-sized body. And in that case, because all the bodies in the solar system orbit in the same plane, in the ecliptic plane, we would expect anything that came out of that collision to match the ecliptic better than the equator, which matches the Earth's spin. So that's one of the many reasons we'll see later on in the semester for why we believe the moon formed from a giant collision with a Mars-sized body. But in any case, let's continue with the eclipses. So at almost every new moon or every full moon, the moon is, let's talk about new moons. The moon is above or below the Earth, and so the shadow of the moon misses the Earth. And at the full moons, the moon is either above or below the shadow of the Earth and does not pass through the Earth's shadow. The tilted orbit of the moon passes through the Earth's orbit around the sun, passes through the ecliptic at 2 points, and we call those points nodes. Let me show you a diagram. This is a really complicated diagram. It's going to take me a couple minutes to unpack it, but it's absolutely crucial to understanding why we don't get eclipses at every new and full moon, why they only happen twice a year, and it also turns out how it is that we can predict eclipses. So let me spend a minute unpacking this diagram. So first of all, here's the sun. This blue line out here, this is the Earth's orbit around the sun, and this body right here represents the Earth. So you can see it in the 4 diagrams. That's the Earth right there, the Earth right there, the Earth right there, the Earth right there. Here's the moon's orbit around the Earth. And the moon's orbit is not in the ecliptic plane right here. The moon's orbit is tilted by about 5 degrees with respect to the ecliptic plane. So there are times when the moon is above the Earth's orbit around the sun and times when the moon is below the Earth's orbit around the sun. Okay? So the moon during the course of the month spends half of the month above the Earth's orbit and half of the month below the Earth's orbit. And it crosses the Earth's orbit at 2 points, and those 2 points are called nodes. At this node over here, called the ascending node, the moon is going from below the Earth's orbit to above the Earth's orbit, and then the moon is above the Earth's orbit, and here when it crosses down below, this is called, not surprisingly, the descending node. At the descending node, the moon is going from above the Earth's orbit to below the Earth's orbit. More properly, it's going from north of the orbit to south of the orbit, and here it's going from south to north. So the moon crosses the Earth's orbit here, and it crosses the Earth's orbit there, and we can connect the two of them, and we form something called the line of nodes. Really what we're doing here is you can think of the Earth's orbit around the sun like a big square flat plane. And you can think of the moon's orbit around the sun as lying in a flat plane. And these two flat planes, like two pieces of paper, intersect one another. And when two pieces of paper intersect one another, when two planes intersect one another, their intersection is marked by a line. And we call that line the line of nodes. Okay? So let's think about that one for a second. So that's the line of nodes. Now, what happens with the moon orbiting around the Earth is that during most months, the moon is either above the Earth, and so its shadow passes above the Earth, and we don't get a solar eclipse. And then 2 weeks later, when the moon is at a full moon, the moon is below the shadow of the Earth, and we don't get a lunar eclipse. And then the very next month here, the moon will still be above the Earth, and we won't get an eclipse, and it'll still be below the Earth. As the moon goes around the Earth and as the Earth goes around the sun, you'll notice that as the Earth goes around the sun, the moon's orbit maintains its orientation. That is, the moon's orbit is tilted, and that tilt always points to some direction in space, at least in the course of a year. We'll talk about in a second the fact that it's actually wobbling around, but let's not complicate it yet. It's already complicated enough. The moon's orbit is a flat plane, and that plane points someplace up there in the sky. And as it orbits the Earth, it maintains that plane. Okay, so here's the moon orbiting in its plane, and it maintains that plane. So for this month, there are no eclipses. For the next month, there are no eclipses. And for the next one, there's no eclipses. But then eventually, we end up in a situation where the line of nodes is pointing at the sun. And what we mean by the line of nodes pointing at the sun, that's a really fancy way of saying, look, as the moon goes from being above the Earth's equator, above the ecliptic, to being below the ecliptic, as it passes through the ecliptic, if at the moment that the moon passes through the ecliptic, that is, if at the moment it passes through the line of nodes, it also happens to be a new moon, then we get a total solar eclipse, or we get a solar eclipse. And then 2 weeks later, when the moon is ascending, going from below the orbit to above the orbit, we'll get a full moon and we'll get another eclipse. But it can only happen when the line of nodes is pointing at the sun. The rest of the time, when the line of nodes are not pointing at the sun, the moon is either going to be above the Earth, or in this case over here, when it is new, it is below the Earth right there. It's only in this special case, when the line of nodes lines up, that we get eclipses. And that happens twice a year. It happens over here, and then 6 months later, it happens over here. And it's only when the line of nodes points at the sun that we can get eclipses. And so if we can get eclipses now, imagine that we have eclipses now. And in fact, that's exactly what's going on. We just had an annular eclipse a couple days ago. So the line of nodes is lined up with the sun right now. That won't happen again for another 6 months. So for the next 6 months, we're guaranteed of not having eclipses. And then 6 months from now, we can have eclipses again. We'll come back to this diagram in a second, but I just want to take a breather right now, and let's do a learning catalytics question. That learning catalytics question is, if the plane of the moon's orbit were in the ecliptic plane, that is, if the moon wasn't tilted at all, it's in the ecliptic plane, how often would we get a lunar eclipse? Would we get it twice a month, once a month, twice a year, once a year, or every day? So go to Learning Catalytics, pause this video if you have to, and answer this question. Okay, so what did you answer here? Turns out if the plane of the moon's orbit were in the ecliptic plane, there would be a lunar eclipse at every full moon. And so the answer to this one is once a month. We would get an eclipse once a month at every full moon. There would be 2 eclipses per month. There'd be 1 lunar eclipse and 1 solar eclipse per month, but this question was specifically asking about lunar eclipses. So the answer there was once a month. So let's see what this looks like in the sky. Maybe I can help unpack this diagram by talking about what happens in the sky. So here's what's going on in the sky. We've got the ecliptic plane right here. This is the path of the sun through the sky. And remember, the sun moves slowly along the ecliptic. It takes a whole year for the sun to go all around the ecliptic and come back to where it is now. Here's the moon's orbit. And the moon's orbit is tilted with respect to the sun by 5 degrees. And the moon takes a month to go around its orbit. So it goes around that blue line every month. Now, what happens in most months is that the sun will be here, and when we get a new moon, that is, the moon is between the earth and the sun, it'll be either above the sun or below the sun. It won't be at one of the nodes, and we won't get an eclipse. But twice a year, the sun is close to the nodes. It would be on the node right here, and then the sun, remember the sun takes a whole year to go around here. So it'll be here. It'll be at the other node on the opposite side of the sun, opposite side of the sky 6 months from now. When the sun is close to the node in the sky, if we get a new moon when the sun is close to the node, then we can get an eclipse, because then both the sun and the moon are together in the sky. And then 6 months later, it can happen again. So that's what's going on here. When in this particular case here, you can see the moon. This is the descending node of the moon right here, because the moon is going from north of the ecliptic to south of the ecliptic. So this is the moon on its descending node. So here's the moon when it's new at its descending node right there. So that sky picture corresponded to this time of the year. And like I said, really what's happening here is it has to happen that the moon is new at the same time that it's passing through the ecliptic plane. Here, when the moon is new, it's above the ecliptic plane. Here, when it's new, it's below the ecliptic plane. But here, when it's new, it's passing through the ecliptic plane. And we can get eclipses, and then we can get eclipses 6 months later. So if you draw a chart like this, and again, this is a little complicated, but let's spend a minute unpacking it. If you draw a chart like this that shows you the years, and it shows you the months of every year, and it shows you when eclipses occur, every yellow dot that you see here is a solar eclipse, and every black dot that you see there is a lunar eclipse, you will notice that the eclipses occur about 6 months apart. Here in 2020, we had a lunar eclipse in January. We had a lunar, solar, and lunar eclipse in June, July. These two were in June, and that one will be in July. And then we will also have a lunar and solar eclipse in December. And you will notice that we had them in January, no eclipses for 6 months. Then we had a series of eclipses, no eclipses for 6 months, and then we had a series of eclipses. And then you would expect that 6 months later we would have the eclipses again. But what's interesting is when you look at when these eclipses are occurring, we call these, by the way, just to confuse students, we call these eclipse seasons. When the line of nodes lines up with the sun, we say that we have an eclipse season because eclipses can occur. The rest of the year, we're out of season. Eclipses can't occur until the line of nodes lines up again. Now, looking at this diagram, you might say if the nodes line up, they will line up again exactly 6 months later, and exactly 6 months after that. And that would be true if the plane of the moon's orbit was still, but it's not. It turns out, just like the Earth is wobbling because the moon is pulling on it, the moon's orbit is wobbling because the sun is pulling on it. And as the moon's orbit wobbles around a little bit, it pulls the eclipses a little bit earlier, year after year after year after year. So in 2019, the summer eclipse season, or the eclipse season, was happening in July. In 2020, it's June and July. In 2021, it's May and June. In 2022, it's April and May. In 2023, it's April and May. In 2024, it's March and April. So you can see it gets a little bit earlier every year. So the eclipse seasons move through our calendar as the moon's orbit sort of wobbles around. But it's predictable. It's predictable when we will get an eclipse. And this points to the fact that humans can predict when eclipses will occur. So the first question is, who was the first person to do this? Who was the first person to predict when eclipses would occur? And that was Thales of Miletus. Thales is an ancient Greek philosopher, and he may be the person, he may have been the first person to predict a total solar eclipse. And he predicted that it would happen in the year 585 BCE. So the story of this prediction comes from an ancient historian, and they're not always accurate. But the story is that Thales of Miletus had predicted that an eclipse would occur in the year 585, and that eclipse happened during a battle between the Lydians and the Medes. And the disappearance of the sun so disturbed the two armies that they signed a truce and returned home. And the story goes that there was a total solar eclipse during this battle. And as I said, it so disturbed the two armies that they signed a truce and they went home. And this eclipse was described as the one that was predicted by Thales. So if Thales had really predicted this eclipse, it would be the first instance in history that someone predicted a solar eclipse. What's also interesting about this is that if this story is true, that there was a battle going on between the Lydians and the Medes, and there was a total solar eclipse during the battle, well, today we can predict exactly what day that would have been, and that would have been May the 28th, 585 BCE. And what's cool about that is that makes it the earliest historical event that can be dated precisely. We know exactly the day of the battle between the Lydians and the Medes because of the total solar eclipse that happened that day. Well, there's a lot more detail into predicting total solar eclipses. And so what we're going to do now is we're going to talk a little bit about how you could go about predicting eclipses. An important thing to know about predicting eclipses, let me go back to Thales for a second, is because solar eclipses at any one location are rare, ancient astronomers learned to predict eclipses by watching lunar eclipses. But I think it's more fun to think about solar eclipses. So let's see if we can predict when solar eclipses will occur. Lunar eclipses, because they're visible to everybody on the night side of the Earth, you will see a lunar eclipse far more often than you'll see a total solar eclipse. And so that makes them a lot more useful for predicting when eclipses will occur. But like I said, solar eclipses are more spectacular. So let's talk about predicting them. When I've showed you these plots, it looks like a whole bunch of crazy lines drawn on a globe of the Earth. And you think to yourself, my goodness, what sense is there to this? What pattern is there in there? These are the eclipses from 1981 to 2000, from 2001 to 2020, from 21 to 40, from 41 to 60, from 61 to 80, and from 81 to 2100. As I flipped through those, did you see a pattern? Did you see anything that looked familiar, that appeared over and over again? Let me play it back again. See if you can see a pattern. 81 to 2000, 2001 to 2020, 21 to 40, 41 to 60, 61 to 80, and 81 to 2100. Now, if you're having a hard time picking out the pattern, I don't blame you. It's not a very obvious pattern to pick out, but let me show you a pattern or something really interesting. Let me phrase it as an interesting thing. We'll see the pattern here in a second. By the way, I should point out, it's a great time to talk about the philosophy of science. This is a lot about what scientists do. When things are predictable, when things occur in cycles, the way we first discover them is we see patterns and patterns that repeat themselves over and over again. So scientists spend a lot of their time looking for repeating patterns because that's a signal that there's an underlying cycle, something that repeats over and over again. And then we go look for that cycle. And then we try and understand what causes that cycle. And then once we know what causes that cycle, we can predict what that cycle is going to bring in the future. That's how we go about predicting eclipses. Lots and lots of science works this way. So if you look at this eclipse path diagram, I hope that you'll notice that there are two really weird eclipses that look the same. You'll notice that there's an eclipse down here on December the 4th, 2021, next year, and an eclipse down here on December the 15th on 2039. And they look almost identical. They look the same. Now, first of all, you might wonder, why do these eclipses down here look so big? Well, the answer to that is twofold. The first answer to that is because of the map projection that they decided to use in this. They're using the Mercator projection, and you will remember that the Mercator projection distorts things at very far northern latitudes. Look at the size of Greenland right here, right? Greenland is not bigger than the continental United States. Greenland is significantly smaller than the continental United States. It just looks really big because we're using a Mercator projection map. Alaska here looks to be, as big as most of the United States, and it is not. And look at Antarctica down here. It looks monstrously huge. It looks like it has as much land as the rest of the world combined, and that's not true. So one of the things that's going on here is the map is distorting the size of these eclipse paths. That's why they look really big. It's a distortion from the map. The second thing that's going on is when the shadow of the moon is hitting the curved Earth. Where did I put my globe? When the moon's shadow is hitting the curved surface of the Earth, it's not hitting a flat, the front face of the Earth where it would leave a nice spot. It's hitting way down here, and that shadow gets stretched out. It's actually very much like the seasons, right? The sunlight down here gets spread out. As that shadow hits the Earth down here, it spreads out across the surface of the Earth. So that's why those eclipse paths look so big down there. That said, although they look really big, the eclipses themselves are usually not very long. They're usually not terribly spectacular eclipses to see. But in any case, let's stop for a second and focus on our pattern here. Here's an eclipse in 2021, December 4th, and here's an eclipse in 2939, December 15th, and they look almost the same. So I want you to answer this question. How far apart in time are those two eclipses? December the 15th, 2039, and December the 4th, 2021. To make it easy to do the calculation, I want you to enter your answer in years, months, and days. That is, calculate how many years, how many months, and how many days go by between December 15th, 2039 and December 4th, 2021. Go ahead, pause this video, go to Learning Catalytics, and answer that question. How many years, months, and days between the two eclipses? All right, what did you come up with? Well, when I look at these two numbers, first of all, they're in 2039 and 2021. So when I subtract those two, that I get there's 18 years. They both occurred in December, so there's 0 months. And one was on the 15th and one was on the 4th. And so it's 18 years, no months, and 11 days. So I want you to write that down. 18 years, 0 months, 11 days. 18 years, 0 months, 11 days. Now, let's look for two more eclipses that look the same. And in particular, I'm going to do two eclipses that are special to me. The very first eclipse that I saw and the very next eclipse that I'm going to see. So you might remember from my previous lecture that I got to see the March 29th, 2006 eclipse. You'll notice that it started here at about 10 degrees south latitude, and then it moved up on the Earth. The maximum eclipse was there at about 20 degrees north latitude, and then it moved up and curved like that. So look at that S shape to that eclipse right there. It turns out there is that exact same shape on April the 8th, 2024. So now I want you to calculate how far apart are the eclipses of April 8th, 2024 and March the 29th of 2006. Again, answer in years, months, and days. All right, so what did you get in this case? Well, let's look at the answer. 2024 minus 2006 is 18 years. April the 8th and March the 29th are about 11 days apart. They're 10 days apart. But so the answer that I come up with is 18 years, 0 months, and 10 days. Well, that's almost the same answer I got before. And in fact, if I did a proper accounting of the number of leap days in there, it turns out that both of them would have been 18 years, 0 months, and 11 days. In fact, every single eclipse on here, every single eclipse is preceded by an eclipse that looks the same 18 years, 0 months, and 11 days earlier. And it's followed by an eclipse that looks almost identical 18 years, 0 months, and 11 days later. Eclipses repeat in a pattern that takes 18 years, 0 months, and 11 days to repeat. And like I said, you can find, you're welcome later on. You can pause this lecture if you want to do it for all of these. Pick any eclipse you want. Just sort of randomly here. Let me pick the one in 2017. So the Great American Eclipse in 2017. We had an eclipse on August the 21st, 2017. So I'm going to predict that 18 years, 11 days later, we're going to have an eclipse. 18 years is going to be 2017 plus 18 is going to be 2035. 11 days later will be August 32nd. Obviously, there's no August 32nd, so that's going to be about September 2nd, 2035. I should see an eclipse that looks on the Earth like that. So let's look for it. And how about that? September the 2nd, 2035, there it is. How about that? 18 years, 0 months, 11 days. So where does that come from? Now that we have found the pattern, scientists need to dig into it, or as a scientist, we need to dig into it and figure out where that pattern comes from. Well, that pattern comes from the fact that two things have to happen for a total solar eclipse. Those two things are, obviously, the phase of the moon. What's the phase got to be for a total solar eclipse? Go ahead. What is it? It's a new moon. You need a new moon. So for a total solar eclipse, you have to have a new moon, and the line of nodes has to point to the sun. Those two things have to occur at the same time in order to get a total solar eclipse. So let's figure out how often those two things happen together. So a total eclipse of the sun only occurs at a new moon, and it only occurs when the sun is aligned with the moon, the nodes of the moon's orbit. That is, when the line of nodes points at the sun. Well, the first thing is the new moon. It takes 29 and a half days to go from one new moon to the next. In fact, 29.53 days. That's the length of time it takes the moon to go through its phases. If the line of nodes points at the sun today, it will take 346.6 days for the nodes to point at the sun again. And this is called an eclipse year. It's not 365. It would be 365 if the moon's orbit wasn't doing this wobble. And the moon is wobbling. The moon's orbit wobbles about almost every 19 years. It's 18.6 years. Don't worry too much about the details. Just know that it's wobbling. And because it's wobbling, the line of nodes only lines up to the sun every 346.6 days. So the thing is, if we get a solar eclipse today where we have a new moon and the line of nodes lines up, we will get a solar eclipse again when these two numbers, when these two numbers match up. Well, when will these two numbers match up again? Let me give you a fantastic example. I'm a big fan of Five Guys burgers and fries. And let's imagine that I eat Five Guys burgers and fries every third day. Okay? And you like Five Guys burgers and fries, and you eat Five Guys every fifth day. So we're both at Newcomb Hall. I'm eating Five Guys. You're eating Five Guys. We notice one another. We wave at one another. And then the question is, when will we see one another eating Five Guys again? Well, if I eat Five Guys every 3 days, that means I eat Five Guys today, 3 days later, 6 days later, 9 days later, 12 days later, 15 days later, 18 days later. I'm eating it 3 days every 3 days. So I'm eating it on the third day, the 6th, 9, 12, 15, 18, 21, 24, 27, 30, etc. But on the other hand, you eat Five Guys every fifth day. So when will you be eating Five Guys again? Well, you'll be eating it on the 5th, the 10th, the 15th, the 20, 25, 30, 35, 40. So here's what happens. When will we be eating together on the same day? Well, on the 3rd, I'm having Five Guys, but you're not. On the 5th, you're having Five Guys, but I'm not. On the 6th, I'm having Five Guys, but you're not. On the 9th, I'm having Five Guys again. On the 10th, you're having it, but I'm not. On the 12th, I'm having it, but you're not. But on the 15th, we're both eating Five Guys again. So that day when you and I see one another in Newcomb Hall and we wave at one another and say, hey, we're both eating Five Guys, I can predict that 15 days from now, we'll see one another and we'll both be eating Five Guys. And I can also post-dict that 15 days ago, we were sitting in Newcomb Hall eating Five Guys together, if we both stick to this very strict Five Guys schedule. 15 days ago, we were both in Newcomb Hall eating Five Guys together. And in fact, if this continues on for many years, we can predict that not only 15 days from now will we be eating Five Guys together, but 30 days from now, 45 days from now, 60 days from now, this pattern's going to repeat over and over again. That's how we predict eclipses. In this case, the numbers were nice and round, 3, 6, 9, 12, 15, 18, 5, 10, 15. In these cases, the numbers are not so round. But it turns out these two numbers, if they line up, will eventually line up again. And the question is, when will that occur? Well, it turns out the ancient Greeks were able to predict this. They were able to calculate when the moon would line up again. This may be how Thales did it. But certainly, if not then, by the time of the Saros cycle, the invention of the Saros cycle in ancient Greece, they knew this. So let's imagine that 223 new moons go by. 223 new moons, that's 223 months. At 29.53 days for the moon to go through its phases, it turns out that is 6,585.3 days. Well, that's also the same as 19 eclipse years. Remember, an eclipse year, when the line of nodes lines up, it'll line up again 346.6 days later. If we take 19 of those eclipse years, they also equal 6,585.3 days. And if you calculate what that is, that's 18 years, 0 months, and 11.3 days. That's why the eclipses repeat every 18 years, 0 months, and 11.3 days. They repeat because after 223 new moons, the moon is back to being new at the same moment that the line of nodes lines up. For all 223 months, for all 19 years in between, they weren't occurring at the same time. So there weren't eclipses occurring, but they will occur again like that. Now, this third of a day turns out to be really important. That third of a day is why the eclipses move on the Earth. So you'll notice that this eclipse was here on the Earth. This eclipse was shifted over. And if you look at how much it has shifted over about 1/3 of the circumference of the Earth. Remember, it takes 24 hours for the Earth to spin. 1/3 of a day is about 8 hours. And so what it's really done is the Earth has had an extra 8 hours to rotate there. And so the eclipse for the next one has shifted to the west by 8 hours. So here's where the eclipse was in 2021. 18 years, 11 days later, it'll be, and 8 hours later, it won't occur in the same place. It'll be shifted over by 8 hours on the Earth. A better way to put it is it'll occur 8 hours later, which means the Earth will rotate 8 hours more, and the eclipse will be a little to the west. Look at the ones that I showed you before, the one in 2006. So 18 years later, we're going to get the one in 2024, but it's not going to occur in this part of the world because the Earth is going to turn for an extra 8 hours. So it'll be 1/3 of the world or 8 hours away. And we're going to get our eclipse on April the 8th, 2024 over here. So that's how we predict eclipses. And just to summarize again, after 223 lunar months, which is exactly 19 eclipse years, the moon is again new at the same time that the line of nodes are aligned with the sun. Now, here's a really important thing to know. You might say, well, wait a second, then why do we get any eclipses in between? If they line up now, and they're not going to line up again for 18 years, 0 months, and 11 days later, why do we get any eclipses in between? And the answer is, at any one moment in time, there are many of these different cycles going on. There are many Saros cycles operating at a time. And so these two eclipses, the one in 2006 and the one in 2024, are part of a family called a Saros cycle. They're all part of the same Saros cycle. This eclipse in 2021 and this eclipse in 2039 are all part of a different Saros cycle. But there are many Saros cycles going on at one time. Okay? So that's why we get many different eclipses, but when you have an eclipse, you can predict when the next one will occur. Now, here's the problem. The next one is 1/3 of the world away. The one after that is 2/3 of the world away. The one after that is 3/3 of the world away. After 3 Saros cycles, which is 54 years and 1 month, the same eclipse occurs, and it occurs in the same part of the world again. And so if we look at this Saros cycle, I saw the eclipse on March 29th, 2006. That was preceded about 18 years earlier in 1988 on March 18th. So there was an eclipse in 1988 in March 18th, and that was preceded about 18 years earlier by an eclipse on March the 7th, 1970. So we get an eclipse on March the 7th, 1970. 18 years, no months, and 11 days later, 1988, March 18th, we get an eclipse. Looks the same, but it's rotated 1/3 of the world away. 18 years, 11 days after that, we get the eclipse that I saw, March 29th, 2006. And then 18 years, 11 days after that, we get the one that I will see next, April the 8th, 2024, cutting across the United States. If you look at a map of the United States, you will see, of North America. You look at a map of North America, and you look at all the eclipses in North America in the 21st century, you will see this 54-year, 1-month pattern repeating. So, for example, here's an eclipse on August the 12th, 2045, August 2045. 54 years, 1 month later. So 54 years, 1 month later. 54 years will be 2099. A month later will be September 2099. We get the same eclipse in the same part of the world. Now, it doesn't follow exactly the same path on Earth because there are other things going on with the moon. You might remember the anomalistic month. The anomalistic month is how long it takes the moon from being closest to the Earth to closest to the Earth again. It turns out it doesn't line up with either the phases of the moon or the nodal passages, and so that's going to also shift this eclipse path a little bit. So there's this eclipse path on August the 12th, 2045. 54 years, 1 month later, there's the same eclipse, September of 2099. How about this one? Let's do our 2017 eclipse. August 2017. 54 years later is going to be 2071. That was in August, so it'll be in September. September of 2071. There is the same eclipse, same cycle, 54 years, 1 month later. How about, let's see. Those are probably the best ones that are on here. This one right here, 2052. Well, that's not going to occur in the 21st century, so we can't see that one. So those are probably our best ones to look at. Well, let's do this one, 2024. So we have 2024. 54 years later is going to be 2078. This is April 2024, so that will be May 2078. So we have this, our 2024 eclipse. You will get to see its partner eclipse on May the 11th, 2078. Make sure you see both of them. See the one in 2024 and then make the effort to see the one in 2078 so that you can say that you have seen two eclipses that are part of the same 54-year, 1-month Saros cycle. That's why I am looking so forward to the 2024, because it'll be the first time in my life that I've had the chance to see two eclipses in the same cycle. I certainly hope I live long enough to see a couple more eclipses in that cycle as well. That is how astronomers predict eclipses. Thank you very much for joining me in this lecture. In our next lecture, we're going to start examining the history of astronomy. We will start with ancient astronomy and move our way up to the ancient Greeks and then eventually the Renaissance. But now that we've talked a little bit about predicting eclipses and we talked about Thales and we've talked about Aristotle, let's learn a bit more about what the ancient Greeks knew about the sky and what the peoples that came before them knew. I will see you in the next lecture.